Okay, before we get started, we're just going to jack that up to about that big. Should be big enough for everyone to see. Okay, so Emlyn, no, I didn't forget to write slides. I was too lazy to write slides. So we're going to do something totally different. We're going to write a presentation together as a Python module. Why not? It's easier than writing slides, and maybe we can have some fun. The title of this talk is More Generators. And I think one of the very first talks I ever gave at a PyData event was about generators. In fact, the very first PyData London that I ever attended in 2013, boy, that's going back a long way. I gave a keynote because the other guy canceled, and so I had the whole audience to myself. And so let's see what we can do now 5 years on with generators. Generators have been around in Python for 15 years or so. Interesting question that I keep coming to is, how come you see people talk about them at conferences and everyone thinks they're such a cool feature, but nobody really uses them? Like, you don't see any big libraries use them as a core metaphor or a core API, other than some of the async stuff. How come it doesn't show up that much in the field of data science? Now, one huge disclaimer. Despite having spoken for now my 5th year in a row at a PyData London and having spoken at 25 PyDatas in the world, I don't really know a whole lot about data science or machine learning. I do mostly scientific computing. I'm more of a programmer than I am anything else. So please, if you don't want to learn about programming, just leave the room. I won't be too upset. Okay, so let's get started. My name is James Powell. This is the Python community, so I really should make sure to include my Twitter handle, or I should put my email here. So I'm James at don'tusethiscode.com. And my Twitter handle is also don't use this code. Okay, so we'll make sure that we print those out so we can get started. Probably the most important things. Now, as you can see at the top of my file here, I have a couple of simple Vim macros just to make my life easier. So as we go through this, I'll be pressing one of those key combos, and you'll see some output at the bottom of the screen. And so let's see if we can use that to kind of follow along. Now, one unfortunate thing here is, because these aren't slides, I can't do the self-promotional thing of getting all of you to follow me on Twitter by having like a big Twitter thing at the bottom of the screen. But because this is Python, we can just overwrite print to always print my Twitter handle every time I print something out. So let's just do that really quickly, and we'll see if this gets annoying or not. We'll say from built-ins import print as _print, so we don't lose the original print. We'll print what we were originally going to print, and then we'll print out, follow me on Twitter at, and then my Twitter handle. Yeah, this is going to be this is going to be 45 minutes, folks. Get ready for this. And let's just put this all the way on the side of the screen. There we go. And let's give this a try with this module and see if it works. Oh, and by the way, we need to make these from built-ins import print as. This is Python 3. That's one small thing we have to make sure that we're using Python 3 here. So we'll just, there we go. Because unfortunately, sometimes, there we go. Follow me on Twitter. Although that's kind of annoying. So what we'll do is we'll just play with this a little bit. This is harder than it looks, by the way. This is much harder than it looks, folks. I'm not faking it. This is for real. If first and first.pop, else, because we want this to be really classy. We'll only put the Twitter handle, we'll only put the full follow me on Twitter for the first time it prints out. There we go. Isn't that fantastic? So hopefully we won't do this for the whole talk because that'll be really tedious. But that's kind of what you're in store for. If you want to leave now, that's OK. Let's give you a quick overview of what we're going to talk about in this session. It took us 5 minutes to even print out the title, so let's see how fast we can go. So the first part, we're going to talk about a little bit of review. The second part, and so this will be part. In the second part, we are going to talk about what generators actually are. In the third part, we're going to talk about why they are not what you think they are. And in the last part, we're going to have some fun. Okay? Now, let's get started with what generators really are. So we'll just create a new file called review.py. We'll grab these from the top. And do you want us to grab the print and really actually have us print out my Twitter handle every slide or every print? OK, good. Neither did I. That's just going to be really tedious. OK, so let's figure out what a generator. You really do want me to do that every time? OK. Otherwise, you might think I'm faking this whole thing. OK, so there we go. So there's our custom print function. OK, I'm going to start off with a very simple question. And since this is so tedious to see on the screen, we'll just zip those out. I'm going to start off with a very simple question for you. My question for you is, what's the difference between these two?
Maybe choose a different color scheme so it's visible.
Yeah, we can try that. You can also sit closer to the front. We'll go colors. We'll do solarized light. Hey, look at that. Thank you very much for your feedback. OK, what's the difference between these two? Got a function. OK, come on, folks. This is like the very beginning. What's the difference between these two?
The first one is constant, the second one is an anonymous function.
OK. Now, if I make this a little bit simpler, and I ask you, what's the difference between these two from the perspective of somebody just using them who can't see the source code? Is there any difference between these two from the perspective of just using these two? They do the same thing, right? They're basically formal differences. And what you could say is, well, if somebody were clever, then there might be some help text on this. And you wouldn't see that help text on the add2 because it's an anonymous function, right? But you'd see the help text on the add, and the name wouldn't be right. But then I'd say, you know what? This is Python. We can just monkey patch this thing, right? And this is name equals add2. And then it really becomes difficult for us to distinguish between these two. And in fact, it turns out that these are just two ways to write essentially the same thing, except there are certain syntactical restrictions to the lambda that we don't have in a normal function. We can't have statements. It's just expressions. Let me throw in another example. And I want you to tell me what the difference between this is, and we'll call this adder. And we'll put a pass here, because we'll use this in a second. OK. How about this one? What's the difference between this structure and the previous structures? Do you see any difference? Still adds numbers. It's just a different formulation. And you might say, well, we still have the problem with the name and the help text, but trust me, we can patch that out. Now, one interesting thing here is you might say, well, there is a difference, because if I have this adder, I can take this code and I can move it somewhere. I can't move the other code. I can do things with it that I can't do with the other one, right? I can do something like this, and I can initialize this to 0. And when I actually run it, I can give it some kind of weird behavior where it remembers some state, because this is an object, and objects are about state, and so now the adding behind the scenes transparently adds something in there. But I'll tell you, what are you talking about? That's nonsense. I can do the same thing with my original add up here, right? And I really didn't do much to change this. And you might say, but James, there's something more. Oops, we've got to make this global, and this should just be. And you can say, you can actually even do more. You can say, I don't really like using globals, even though that's the same. And, having this global state, it's not encapsulated. And I'll say, oh, it's not encapsulated, is it? Well, can I do this? I just add it to the function, right? Functions in Python they have a little dict, so you can see behavior is the same. And you might say, but if you're being really clever, you could make two versions of this, and they operate separately. Because it's a class, classes can create instances, right? And because classes can create instances, we can have two of these, and they both have independent state, right? And I might say, yeah, but why can't I just do this? And then I don't even need this crazy thing here. I just use non-local. And then we finally get tired of this exercise. And what we realize is that what we have discovered here is a fundamental principle of computer science. Namely, and I'll finish the example before I tell you what the principle is. Boy, I must be very concentrated to be able to talk and code at the same time, huh? Who's impressed? I hope some of you are impressed. This is really, really hard. This is really hard. Okay, so and we're done. So we can see exact same thing. And in one case, we have a closure and a function returning a function. In the other case, we have an object. And we've now discovered firsthand, by trying to tease apart some differences, a fundamental principle in computer science, which is objects and closures are identical. There's a clear equivalence between them. Let's park that for a second, and let's talk about something slightly different. Here's what we're going to talk about that's slightly different. Let's pretend that we have a function that computes something. And because this is hard enough as it is, I'll just give you a dumb compute function that doesn't do anything that interesting, but it takes 1/10 of a second to run. Right? So it returns a random number between 1 and 10, and it takes 1/10 of a second to run. See? You can even feel that. You can even feel that 1/10 of a second there. Now, I can have a function, just a regular old function, that maybe does a couple of computations in a row. So maybe it calls this function 10 times. Right? And I can print out what this function does. And we can see this in action. It should take about a second, and you can see it takes about a second. Now, I can look at this and I can say, that's very interesting. It takes a full second. It computes everything up front. And I can use what I learned up before to see if I can just take this code here and put it into my class formulation. Right? There we go. And again, if I do this, you can see this. Oh, we have to, of course, we'll put a markup here. There we go, and you can see they both do the same thing. Now, one thing that I can notice is that typically, when I actually want to use this, I'm just going to iterate through the values, right? And we'll put a markup here just so we can. The last time I did one of these presentations, it went on YouTube and got 300,000 views. And then some people in the comments were like, wow, he's really good at using Vim. And then some guy's like, he's such a noob. His Vim skills suck. He doesn't even use VIP for visual in paragraph. And I'm like, okay, got to step up my game. So I'm trying to step up my game here. But you can see, this is the example. It really happened. The YouTube comments are harsh. They're always very harsh. But you can see we have the same equivalence. Now, something interesting we can see is because we're iterating over this, one thing that we might know is that in Python, whenever we have a structure that looks like the following, we know that behind the scenes, Python turns it into something that looks like the following. And then there's like a try here, and then you try and get the next value out of the iterator. The xi stands for an iterator for that. And you accept the stop iteration and break. So we know there's an equivalence here, and we know that if we implement iter and next, we can do something kind of interesting. So I'll show you what we can do. We can create our own object that's iterable. We'll say that it's its own iterator, and in the next, we'll just return the next value. Well, what we'll do is in the iterator, we'll just keep track of the size of the computation we want to do, which is 10. And in the next, we'll just say if not self.size, raise stop iteration. Otherwise, decrement self.size, and just return this. Right? And now, if we look at this, and we no longer need these here, if we look at this, we have, and we have to go back up to our mark to run everything. We can see it does the same thing. So what we've discovered here is that there's another concordance here, that we can swap out calling something for iterating over something. But if I were to tell you, and we can see that this result is actually a lot better, because one thing that you notice from the two variants, if I give you these two variants side by side, there's one thing that I want you to notice. And this is one of the keys that people first learn when they learn about generators. And see if you can notice it. Okay, did you notice something? Let me put a break. Let me put a little visual break between the two instances of these two functions. I want you to tell me, really quickly, anybody sees a difference between these two formulations. Because all I've done right now is kind of played around with sticking some code in a different place. Anyone see something really visually different there? One's immediate and the other one is streaming. What we've discovered here is we've discovered some laziness. Now, something kind of interesting occurs when we think about generators in Python, because there is some distinct advantages to this second form. Namely, one, notice there's no storage. We're just doing one computation, returning the value. Here, there's storage. Notice number two, we're getting the values only as we need them. So if we only looked at one value, the top version takes all of 1 second, and the bottom version only takes 1/10 of a second. See, that first one took the entire time. It was eager, did the whole computation, then gave us the whole results. We threw away 90% of it. The second one only gave us the results as we wanted. So we can say, oh, that's really interesting. That's a lot more efficient for both a memory and a time perspective. We're customizing what resources we use in terms of computational time and memory to exactly what the user wants. And the whole nice thing about generators is, generators are this idea that you can write a formulation, the above, but without all of this tedium. So we can just write this here, grab our code from here, and we can see this generator formulation here and this class formulation here are just as equivalent as this function formulation here in a class and this raw formulation here. So what we can see is that generators are a way for us to very conveniently formally describe a structure that performs a computation on demand, where internally the structure itself looks very similar to something that has an iter and a next employed. Okay? So that's our review. I hope that was well within what all of you know, because that's just the start of where we're going to be. Let's take a look at, is anyone lost? Okay, good. Let's take a look at next. What are generators? So one of the things that we saw from that example, and while I grab the top of this file here and my print statement, which we didn't use because I wasn't highlighting it each time, but we'll use it by the end. And we'll just hide some of this stuff because it's little garbage on the screen. Hide that and hide this. What we saw is that we saw immediately some laziness versus eagerness. One of them runs to completion. One of them does the entire computation. The other one eagerly gives you the computation as you go. And what we saw, and what we might also know, is some kind of pipelining mechanism. So one of the things that we see from that generator is the generator only gives you values as you ask for them. So if we take our compute, let's just copy our compute over. If we have, actually no, how about this? From review import compute. Oh, look at this. This really is now a Python package, not just a module. I'm doing this off the top of my head. Come on. Got to give me something. Oh, let me just do this. And let's call this. Okay, there we go. Because the other module has it at the top, now everything's going to have this. Isn't that great? Let's do this. Print equals. That's going to be so annoying. That's going to be so annoying. Okay. So what we're going to do is we're going to do a little bit of, we're going to be nice to you, because that's just going to annoy you. And we'll just move this out here to the top. Okay. There we go. So what we can see is we have now an infinite sequence, right? So if I say for x in f, print x, I now have an infinite sequence, which would be very difficult to mod or eagerly because you can't store an infinite sequence anywhere. And what we know from this is we can do all sorts of cute little pipelining things, just like at the shell, things which approximate the kind of data pipelining that we often do on fancy platforms like Hadoop and Spark and whatnot. And we know that Python gives us the itertools module, and the itertools module gives us a lot of helpers. So we can do things like take a generator and t it to make copies. We can enumerate that to get, the index of it. And then we can do something like slice each of these. So we can offset each of these by an amount. And then what we can do is we can zip them together. Let's put the star here. Make sure we have enough closing parentheses. We can zip these together. And this is a very useful tool called nwise that gives us pairwise views of some structure, right? So I'll show this to you in action. You can see just using what's in Python, we can get like pairwise views. We get A, B, B, C, C, D. And we can even take this further, and we can do fun stuff like getting windowed averages, which is just the sum of these values divided by the length of these values for some values in a windowed size of whatever we want. And so now we can take all of this fanciness, and we can do windowed averages of f of some size. Let's do windowed averages of size 3. And now we have a lot of little helpers in a very terse, almost functional form. You can see it's processing an infinite sequence of numbers and getting like the 3 windowed averages, right? We can do moving averages. And that's really cool. But there's more. There's one other thing that we might have noticed, and I want to ask you, has anyone ever seen an API that looked kind of like this? Let's do this 3 times. There was some function that you had to run first. There was some function that you had to run second. And there was some function you had to run last. And you had to run them in those orders, otherwise it would be, total anarchy, cats and marrying dogs, crossing the streams, absolute chaos. You had some API that's really order dependent, and it's so easy to screw up because there's nothing enforcing that order. Well, one thing that we also know about generators is that they are a sequencing mechanism. So we can take all the code that we wrote here. The average programmer writes, 100 lines of code a day? And we're already at 200, so you're really getting your money's worth, folks. We can do this, right? And fi will be an instance of this generator, and we can do this. And you can see we get sequencing, except we can't screw it up. And we might even know that in Python 3, 6, and later, we have this async await structure. So we can even do stuff like this, create tasks that yield and print some message out. And we can write our own scheduler and right? And we can just do something like scheduler, task, hello, task, goodbye, and we can see it. We can see that this sequencing is actually very important. It's key to why we have generators as the async mechanism in Python for single process asynchronous. You can see that what you have from the scheduling is the yield is actually doing literally what it says, yielding control back to the scheduler, and the scheduler is figuring out how to interleave these. So this is why generators work this way. Now, let's talk about something else. Let's talk about why generators don't appear in PyData talks, why I'm the one who's given this, and it's not just because that's all I know. That is one answer. This is really all I know. I wish I could give a talk on machine learning. I'm sure it would be interesting, maybe as interesting as the average machine learning talk is, which is not very. We're really going off the rails here, aren't we? I will say that one thing that we don't see at PyData conferences, that we don't see in the world is, out there's probably like 1 million biologists whose state-of-the-art tool they're using is Perl. And so a tool like generators is a step. Python itself is a step beyond what they're doing. And Python with generators, they're doing a lot of text processing on like DNA sequences and looking for substring matches. And maybe this is an appropriate technique for them, but we don't see this in the world of scientific computing or numerical analysis. And I'll give you an idea why that is. One problem is that fundamentally, even though this is a very nice lazy mechanism, Python is pretty junk at doing anything numeric computing related. So I'll show you a very simple example. Let's just time 2 operations. We'll time using this generator and this windowed average mechanism against, and I'll get this code from up here because I don't really want to cut and paste. I don't really want to import that. We'll time this against just doing an operation on like a NumPy and D array. Random, import random, and we'll just create a random NumPy and D array with the values from 0 to 10 of size 1 million, okay? And what we'll do is we'll just do, very similar to how the nwise up there works, we'll just do something like this to get the windowed views, and we'll just divide by 2, and we'll see how long this takes. make sure that we have nothing missing in this. Oh, and then we have to do dot time it. And we'll only run this 5 times because it's not going to be that fast. Okay, and you can see it took like 0.1 seconds here. And we'll try the same thing with our generator approach, and we'll see what happens. And it's not going to be very good. It's just that Python integers and Python lists or even Python generators are just not a very good tool for any sort of numerical computation. You can see why, as a tool, these don't really show up when you're doing large, stream multiplications or vector operations. We'll just take this from here. Take that from there. We don't need this, do we? We don't need that. And we'll just say from random import rand range, xs equals rand range from 0 to 10 for this in range. This is like an interview. This is the hardest interview that means the least I've ever done. And we'll do this, list, windowed. I hope if I ever interview at any of your companies, you ask me exactly the questions that we're covering in this presentation. But we'll see how fast this is, and we probably need to make sure we type this right. Have you ever seen anyone live code this much code and get it right? I've never done this before. This is really special. Well, you can see the speed of these two things. Boy, this is slow. And windowed average. Let's try that one more time. Let's see. It's really, really, really slow. Even the construction of you can see it's like 2 seconds versus 0.09 seconds for a million integers, right? So you can see, even at very large scales, if I make this a billion, yeah, we have easy memory use, but if you want to do anything numeric involving large streams, just use a NumPy ND array. It's cache coherent. It's packed into memory. It's just going to be faster. This generator approach and using lists and Python integers for anything that's mathematical in nature, it doesn't work. So I think this is one of the reasons why we don't see generators being used as part of data science libraries in this kind of numerical stream processing sense. Because if you're doing text processing, you're a biologist, and the computational part of your computational biology isn't really that computational, yeah, it's a great tool. If you're doing serious machine learning or models or deep learning, it's not actually a very viable tool because it's hindered by the poor mathematical support in Python itself. Python is an orchestration language, a glue language, and a mechanism like generators is not going to give you the ability to do that much. But let's look at the last part of our presentation. We have 15 minutes. Let's have some fun. Because if we really think about it, when we go back to what we learned about generators in this second section, and we think about this sequencing, what we can see is that generators are a mechanism that can fit into orchestration. They can allow us to give a structure to a program that the program might not already have. They're not necessarily a computational mechanism. They're not about doing very quick vector operations, because NumPy can do that way better. And if it's out of memory, you have other tools that can do out of memory. Julia can do out of memory operations as part of the core language. What you might think, though, is generators might be a tool for structuring a program. And what's a common non-mathematical structuring for a program? What about a graph, right? We've seen this. These used to be all the rage like a year or two ago. I don't know why they're not that popular anymore, but the idea that you can take some equation and do it as a graph, and if each of the nodes are very hard to compute, you can minimalistically recompute the nodes to get some result. So let's think about some operation where we'll do this very simply. We'll do something like this. Do I really have 10 minutes? Because I'm going to need 10 minutes to finish this. Okay. What we're going to do is we're going to build, in the next 10 minutes, a graph computation framework in about 70 lines of Python using generators. So what we might have is we might have some term, and the term is just a generator that yields its own value, and and new value. And this is going to be really, really sloppy, so we can always improve this slightly. We'll do something like this. Okay? So this is just a generator that can take new values. It's just a little computational unit. And we're going to fit it into a larger structure. And maybe we'll do simple addition of terms. Okay? And this, again, will be something where we set the value to none. And what we'll do is we'll do like a while true. And we'll say value equals sum of next t for t in terms. Okay? And you can see we can do add term 1, term 2, term 3. And by virtue of these being live computational units, we can say for x in q, print x. Or actually, we'll do it like this, while true, print next eq. Okay? Now, every time we do this, we do a loop. But and we have to yield the value. So we'll do yield the value. You can see we just yield this value. And if we want to, we can make this a little bit easier to read. So we'll just say from itertools import count for step in count. If step equals 2, we'll actually inject a value into one of these. T.send, and we'll send the value 10 in instead of 1. And then if step equals 5, we'll break out of this. Okay? So here you can see it's even reactive, right? We can send something in and it recomputes. But it's not lazy yet, right? And there's a couple of kind of irritating things that we have to do with this. You'll see the first few values are not quite correct. Now, it's not lazy, and we want to make it lazy. Now, one problem is, unlike Python functions, a Python function, one thing you might have noticed is you can define a Python function like this, and you can throw attributes on it. You can't do that with a Python generator instance. You can't throw attributes on it. So here we'll need to continue to use the generator formulation, but we'll wrap it in a larger object. So what we'll do is we'll create just a very simple decorator, and we'll call it wrapped. And we'll have a class here called wrapped. And we'll just wrap our generator. So we have a place, a storage place, to put something like this. And we'll pump it. This is one thing you'll find with these coroutines. You have to pump them, and we don't have time to talk about this. We'll do something kind of interesting. We'll send our self into this, so we can do something like this. At the top of each of these generators, we can actually keep track of the state of it itself. Okay? And the rest of this is fairly boilerplate. And we won't implement the entire protocol. Okay? And we do something like that. Now, as we do this, we can do the following. We can say, actually, no, we already did that. So what we can do is the following. Here, when we have the terms that we're adding, we might say for each term, we can say t.subscribers plus equals 1, and we can keep track of how many people are subscribing to these values. So we know if we're dirty or not, and we know how many people are waiting to see values from us. Then, what we can do, and this gets really hinky, but what we can do is we can say, in this new term, and we'll just clip this to 0. We can always, every time we yield a value, we can just decrement by 1, so we're no longer a dirty value. And then what we can do is we'll use our same trick from before. We'll put a little sleep in there just so that we can see the dirtiness take effect. Here in the term, what we can do is we can say, whenever we recompute the term, we can mark ourselves as dirty, and we can sleep for some period of time. And so what we'll see is, as long as we're not dirty, it'll just instantly recompute. If we're dirty, this represents a small but very large chunk of a computation, like a deep learning model that's connected in a graph up to something else, right? Some learning model that takes a few seconds to run, but it only is run, and the graph only recomputes it on demand as we go up. Here, in the add, it's not that hard what we have to do. We just have to say, if any of our terms are dirty, we just mark ourselves as dirty, and we recompute our value. So we'll only recompute our value here, but we will compute it once up here. Okay? So let's see if this thing works. This is going to be real pain to debug if it doesn't. And then we'll just set seconds equals to 0 so that most of these are instantaneous. And then what we'll do is we'll actually, the one that we tweaked, we'll see. And then functions not iterable.
You'll indent your done methods of the wrap class.
Oh, thank you.
There you go.
And I have to, wow, you're really paying attention, Emlyn.
I knew anyone was going to get asked questions.
Okay. And then we got to do one more thing. This is going to be, and we yield our value here, and we yield our value there, and routine terms. We have to decrement this up here. We'll also decrement it for dirty here, and let's see if this thing works. Send, and there's one last thing that we're missing. So I'm not stupid. I did actually prep a little bit of this ahead of time. We'll just grab from my prepped version. Yeah. So we'll just grab my prepped version here. Oh, we actually have to use our wrapped class as well. Let's see if we can continue. Let's see if we can continue with this without screwing this up too much. But if not, we'll switch over to the canonical version that I did. I mean, I did actually practice this thing. I'm not doing this all off the top of my head. Okay. So we'll switch over to the canonical version real quick. And we'll just remove this code here, set paste, grab the code from my canonical version, which I promise you I haven't been cheating the whole time on. And we'll move on. And what we can see through this approach is that paste this. Okay, so we'll go to more generators sheet. Yeah, I do know where we're going with this. We'll just grab this code here, and I'll show you this in practice. And this version was the final version that I wrote in preparing this, and I'll show you the final version because I don't want you to have to suffer too much of reading through me live code this. It's going to be real difficult to debug. There we go. But this is the final version in about 82 lines of slightly harder to write than live coded on stage. What we can see is down here, this generator, it'll pause for 10 seconds when one of the values is updated. And the extra 20 lines of code mean that it also will, it's a graph computation framework, so it'll also graph the thing. So you can see this is our add. This one's a much harder computation. There's an add connected to another add. We'll close it, and you can even see the terms go dirty. That's like the 9. You can see that's the 1 second wait for it to do the recomputation. And it's happening at each of the levels, and then it should, you can see that one went dirty. And then you can see each of the results are now faster again because it's not recomputing. And you can see the dirtiness propagate through the network. About 100 lines of code using a generator as your fundamental organizing structure. And I'll show you all I added here was not that much. The only thing I added here was a little bit of an additional mechanism to use network X to draw the thing. And I guess it's a little bit easier to do 5 minutes before you get on stage than when you're on stage. But for the most part, you can see this code is essentially the same. It's just a generator that yields its values, that waits for it to be signaled as dirty, and then results. And you can see this generator is actually an interesting structuring mechanism for larger code. By itself, it's not an interesting computational mechanism, but with tricks like this, you can form interesting structural things. Because each generator, by virtue of being an object that represents a computation, it can also do neat things like, if I had 3 generators in a sequence, I could have them self-elide themselves and fuse into another one. This is the second example I wanted to do if I happened to be running faster than I thought I would, which is to show you how you can have a pipeline of 3 generators that automatically rearrange themselves or fuse themselves with another 20 lines of code. And it's actually not that difficult. And you can see the API here. Maybe it's a little hinky, but it gives rise to thinking about formal structures in their code. And I say, even though this API is somewhat hinky, a comparable graph formulation framework that does just these two pieces is going to be at least 200, 300, 400 lines of code with generators and a little bit of knowledge of how they fit into how Python objects work and the structuring behind them. I mean, I have 95 lines of code here for a graph computation framework. Not too bad. And I almost got it right on the first try live coding it. So I hope you enjoyed that. That's more about generators. Thank you so much.